I'm fleshed out thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into front-end architecture for my Next.js e-commerce platform, server components, state, and data flow. Front-end code bases have a characteristic failure pattern. It's not a sudden collapse. It's a slow accumulation. A component that was meant to display a product card also fetches the product, manages loading state, handles the add to cart action, and traces an analytic event. It works at first. 6 months later, the same pattern has spread. Most components do several things. Nobody is sure which component is responsible for which behavior. The fix is not a rewrite. It's an architecture that decides responsibility up front. For my Next.js e-commerce platform, the architecture is a 5-layer component pyramid. Server components for data fetching, server actions for mutations, and a state model that classifies each piece of data into one of 4 types. This video walks through the full front-end architecture. Let's go. So what we have here is the component responsibility pyramid. Every component in my application belongs to exactly one of 5 layers. Each layer has its own kind of job. Dependencies flow downward only. An upward import is always wrong. At the top, route controllers, 3 to 5 lines. Their only job is connecting a URL to a page component. No logic, no data fetching, no state. Below that, page components. Pages define the layout structure of a screen. They compose feature components without implementing any workflows themselves. A page reads like a table of contents. It tells you what sections exist without revealing how any of them work. Next, feature components. This is where the application lives. Features implement user workflows end to end. They call server actions for mutations, manage the state required for their workflows, and handle user interactions. A feature does one thing: the coupon application form, the checkout flow, the subscription list. Below that, there's entity components. Entities are pure visual representation of domain objects. They receive type view models as props and display them. No API calls, no business logic, no state management beyond trivial hover states. Have primitive UI components, the design system building blocks, buttons, cards, modals, inputs, completely domain agnostic. They change only when the design system changes. The rule at the bottom of the slide says it precisely. A feature may use an entity may never use a feature. If you draw an arrow from an importer to the imported, and that arrow points upward in the pyramid, the import is wrong. The pyramid in practice. Let me make this concrete with examples from my platform. The file path tells you the layer, the domain, and the type. No need to read the code. Route controllers, shop route, export default. Yep, you see this? Beautiful. That is the entire file. The page component renders featured products and the product grid. It defines the layout, 2 sections without knowing how either work. Feature components. Apply coupon form.tsx calls the apply coupon server action. It manages the coupon code input, the loading state while the action runs, and the success or error display. There's one workflow. Entity components. A subscription card TSX receives a subscription view model as props and renders the plan name, status, renewal date, and formatted price. Pure display, no API calls. Primitive components. Button.tsx accepts variant size, loading, disabled, on click. It knows nothing about subscription, coupons, or checkouts. The decision line sums it up. Features, checkout, UI, apply coupon form, TSX tells you the feature, the checkout domain, the UI component. The architecture is visible in the directory tree. Server components reads without the overhead. In a traditional single-page application, data fetching requires a state management library like React Query, an API layer, and careful cache invalidation. Look at the left of the slide. A product page would use query, a loading state, an error state, auth headers, cache configuration. That's the overhead cost of every read. The right side shows the same page as a server component. It's an async function that reads directly from Supabase during rendering on the server. The result is sent as HTML to the client. No client-side fetch, no loading spinner, no cache to manage, 0 JavaScript shipped for this component. The boundary is clear. server components for reads, client components for interactivity. A server component can render a client component as a child, passing server fetch data as props. The client component can call server actions for mutations. Data flows downward, actions flow up. The decision, server components for all data fetching, no React query, no API layer, no loading state. The data is part of the server rendered HTML output. Now we're going to move on to server actions, mutations without REST. Server actions replace traditional REST endpoints for mutations. The left side shows the traditional approach. A fetch call to API checkout, with a method, content type header, an authorization bearer token, a JSON body, and error handling that requires parsing the response manually. The right side shows a server action, marked with use server. It runs on the server. It calls schema.saveParse on the input. If validation fails, it returns the given message. OK, false immediately. If it passes, it writes to Supabase and returns OK, true, and the order ID. The client imports the function and calls it directly. There's no URL, no headers, no fetch call. Errors are returned as structured objects, not thrown as HTTP exceptions. The client pattern matches on OK and calls show error if the action failed. The decision, server actions over REST for mutations. Type functions, no URL, no auth headers, structured results, errors returned, not thrown. Beautiful. Now we're going to talk about the state architecture. We have 4 types. Every piece of state in my application is classified into one of 4 types. Every type has exactly one correct home. Mixing type is the root cause of the most client-side bugs. Firstly, we have server state. Source of truth is Supabase. Owner is the server component. Fetches during render. Read only on the client. It's never stored in use state or context. Some examples we have are product listings, order history, and user profile. When you need fresh data, you navigate. The server component refetches. We have application state. The owner is React context. This is shared across routes. It persists during the session, only for data that is genuinely needed to cross route boundaries. Examples, the shopping cart, authenticated user identity. And we have UI state. The owner is use state, local to one component. Never lifted unless a sibling needs it. Never put into context. Examples of this is a modal open or closed, an active tab, the current value of an unsubmitted text input. So we also have derived state. The owner is use memo or a plain function. Computed from other state, never stored. Storing derived state creates synchronization bugs. The stored value goes stale when its source changes. Examples of this is the cart total or the cart total, formatted price, subscription status. The rule, if it comes from the server, it's server state. If it's shared across routes, it's application state. If it's local to one component, it's UI state. If it can be computed from existing state, derive it, don't store it. Now, we'll move on to data flow. Downward reads, upward writes. Data flows in 2 predictable directions. The downward flow on the left carries data from the server to the UI. So from Supabase to the server component, which fetches during render, to the client component, which receives server fetch data as props, to the entity and primitive components for display. No client-side fetch, no cache to manage. The upward flow on the right carries user actions back to the server. A user interaction triggers a client component, which calls a server action. The server action is validated with Zod and writes to Supabase. A structured result is returned to the client. The client updates its state. The 2 flows meet at the server component and server action boundary. The server is the source of truth. There's no cache to invalidate because server components refetch on navigation. There's no manual state synchronization because the server owns the data. The decision line captures it. Server components for all data fetching. No client-side cache. No loading state. 0.js shipped for read-only components. File structure. Feature slice design, which was a big influence on how I structured this project, right? The file structure of a front-end code base is its architecture made visible. The left side shows the directory structure. App contains the route definitions and layouts. Feature contains the workflow implementations. Checkout, auth, each with its own server action and client components. Entity contains domain, entity display components with their view model types. Shared contains design system primitives, the Supabase client, and utility functions. The right shows the import rules that enforce the pyramid. Features can import from entities. And shared, features cannot import from other features. Entities can only import from shared. Entities cannot import from features. That would be an upward dependency. Shared imports from nothing, app can import from all 3. 2 rules marked correct, 4 marked violations. The import rules are the pyramid made mechanical. A linter can enforce them. The decision, feature slice design makes the pyramid visible in the directory tree. A new developer identifies any component's role from its file path alone. Error handling at 3 levels. I handle error at 3 levels, each scoped to the smallest context that can handle them. The first level is inline component. A single field or form, a try catch inside the server action catches the error and returns a specific message. That message is rendered exactly where the user is looking. Example, this coupon has expired, shown under the coupon input, not in a toast at the top of the screen. Okay, level 2 is server actions with Zod. The scope is a single mutation. Zod's save parts catches invalid input before any database call. A structured field level error object is returned. The client renders the error on the specific field that failed. And here's an example. So for level 3, we have route boundary, the error.tsx file. The scope is the entire route segment. Next.js error.tsx catches unhandled render errors for the route and displays a recovery UI with a retry button. Example, a component throws during render. The user sees a recovery screen, not a blank page. The decision, layer errors from smallest to largest scope. Field level errors stay at the field. Route level errors show a recovery page. Never swallow errors silently. Performance, what Next.js handles for you. 4 performance optimizations that each require manual implementation in a traditional single-page application. Next.js handles all of them at the infrastructure level. Route-based code splitting. Each route's JavaScript bundle is loaded independently. The admin dashboard code never loads for a buyer browsing the shop. No manual Webpack chunk configuration. Server components to Zero.js. Components that only read data are rendered on the server and sent as HTML. No hydration. No JavaScript shipped for read-only components. ISR plus edge caching. Blog posts and product pages are pre-rendered and served from Vercel's Edge CDN. No origin request for most page views. We have Next image optimization. Generates responsive sizes automatically. Lazy loads off-screen images. Serves WebP and AVF. No manual CSR set. No cloudinary pipeline. The decision, structure components correctly. The framework handles code splitting, caching, and image optimization at the infrastructure level. No manual Webpack config needed. We're going to do a little summary here. Structure decides responsibility. And here are 5 key takeaways. The 5-layer pyramid, route, page, feature, entity, primitives. Each layer has one kind of job. Dependencies flow downward only. Upward imports are always wrong. Server components for read, server actions for writes. Client components for interactivity, clean boundary, no client-side cache to manage. 4 state types: server state and Supabase and server components, application state and context, UI state and use state, derived state computed on demand and never stored. Each has exactly one correct home. Feature slice design. The file path is the architecture. File path names tell you everything before you open the file. Error containment by scope. Field level inline. Mutation level structured return. Route level error.tsx. Errors stay at the smallest scope that can handle them. For a client, the front end on this platform follows an explicit responsibility architecture. Each component has one kind of job. Dependencies flow in one direction, and the file structure reflects the architecture. A new developer can identify any component's role from its file path alone. Adding features does not erode the structure. I'm Fleshed Out Thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing front-end architecture for your own platform, reach out. I'm open to freelance projects and consulting. The full post is linked in the description. Complete component pyramid, state classification matrix, and file structure walkthrough. Next in the series, data management, classification, retention, and GDPR erasure. I'll see you there.